Hello everyone, my name is Ravi Jayaratne. I am from University of East London, UK. Today I would like to talk about modeling of Krakatoa tsunami wave propagation and community engagement based on SWOT analysis in Southern Lampung, Indonesia. First of all, I would like to introduce my collaborators of this project or the co-authors of this abstract and presentation. Mohammed Fauzi from Institute Technology Sumatra, Indonesia, Dr. Hendra Achari from Institute Technology Bandung, Indonesia, and Professor Tomoya Shibayama from Waseda University, Japan. Motivation and background of the study. One of the major tsunamis generated due to volcanic eruptions in Indonesian history was from the explosion of Krakatoa volcano in August 1883. It was reported that a 37-meter tsunami wave destroyed 300 coastal towns and villages with over 36,000 casualties. More recently, on the 22nd of December 2018, caused an avalanche from the Gunung Anak Krakatau body into the sea, causing a tsunami in the Sunda Strait. Coastal villages in Lampung in Sumatra and Banten in Java provinces were affected, resulting in 437 casualties, about 32,000 injuries, and over 16,000 displacement. Takabatake atoll conducted a field survey in Lampung and west coast of Java in 2019 following the December 2018 tsunami. They reported that they have severely damaged villages in the southern part of Lampung. For example, East Way Muli, Central Way Muli, and Kunjir. You can see the wave run-up and inundation heights for these three villages. There is no advanced tsunami early warning system due to volcanic eruptions for Krakatoa in Indonesia. Presently, the tsunami early warning system is for submarine earthquakes and monitored by ocean buoys. The left-hand figure illustrates the map of Sunda Strait and its islands, and the right-hand figure illustrates the aerial view of Krakatoa volcano in Indonesia. Project objectives: to carry out detailed field reconnaissance surveys to explore the current status of the coastal defenses, evacuation routes, and high ground locations in Lampung province, including neighboring islands, for example, Sulawesi and Lagundi Islands. To develop a numerical simulation model for wave propagation in the Sunda Strait to simulate past tsunami events, for example, 22nd December 2018 tsunami, and probable future tsunami conditions. Use a decision-making technique called SWOT analysis to combine with the field survey results, the numerical model outputs, and published information to make recommendations for the resilience of local coastal communities for future tsunami events in the area. As I said in the previous slide, one of our main project objectives was to carry out the field surveys. So the top two figures illustrate the damaged buildings in Lagundi Island during the 22nd December 2018 tsunami. The middle two show the setting up evacuation routes and exploring high ground locations in the same island. The bottom figure shows the educating the island community on how to evacuate during a tsunami event. Our second objective was to develop a numerical simulation model. So we used CG wave model, which is a two-dimensional wave transformation model, so which can predict the wave hydrodynamic properties such as wave heights, velocities, pressures, radiation stresses in the complex shapes and depth variations. So this particular model is based on elliptic point slope equation, can simultaneously simulate the effects of wave processes such as refraction, diffraction, reflection by bathymetry, the effects of coastal structures, the energy dissipation due to bit friction, as well as braking. It is applicable for a wide range of wave frequencies. The input conditions of the CG wave model are the offshore wave amplitude, wave period, its direction, and coordinates of the near region finite element mesh. The bathymetric data in Lampung was obtained from GEPCO, which is a global terrain model for sea and land with 15 arcsecond intervals. The tidal data from Panjang Tidal Station, which is located in the Banda Lampung area, was used to estimate the arrival time and maximum wave height at Panjang due to the 22nd December 2018 tsunami. The figure shows the spatial extent used for CG wave model. About model results. The top table shows the recorded tsunami wave characteristics at Banten tidal station, the first and largest tsunami wave, against the arrival time and the wave heights. The first tsunami wave recorded was 0.732 and time taken to reach the Banten tidal station from Krakatoa World Canoe was 3,420 seconds, which is 57 minutes. The bottom table shows the simulated wave heights at nearshore boundaries, for example, East Way Muli, Central Way Muli, Kunjir and Banten, against wave amplitude at offshore boundary 0.5 meters and 0.6 meters. Also, the arrival times taken as 3,120 seconds, 3,420 seconds, 3,720 seconds. It is evident from the above tables that the simulated wave height at Banten at an arrival time of 3,420 seconds was 0.9 in comparison with the recorded value of 0.732 meters. This confirms that CG wave model can be applied for simulating past tsunami wave conditions with reasonable accuracy. The modeling results of an offshore wave amplitude of 0.5 meters give a tsunami wave propagation direction that agrees well with the findings of Takabatake et al.'s 2019 work. Based on the selected offshore wave amplitudes, for example 0.5 and 0.6, the CG wave model predicts large wave heights, hence considerable damage, at nearshore boundaries of Southern Lampung compared to the small wave heights, least damage, in northern areas such as Banten. Two figures illustrate the wave heights against distance along the different transects from offshore, for example at East Way Muli, Central Way Muli and Kunjir. As the offshore wave amplitude increases from 0.5 to 0.6, the wave heights also increase along the different transects. The top two figures illustrate the comparison of wave height distribution from CG wave model for different offshore wave amplitudes 0.5 meters and 0.6 meters by keeping the same arrival time of 3,420 seconds and wave direction of 45 degrees. The bottom two figures show the comparison of wave height distribution for different arrival times 3,120 seconds and 3,420 seconds by keeping the same offshore wave amplitude of 0.6 meters and wave direction of 45 degrees. So in general, the wave heights at East Way Muli, Central Way Muli and Kunjir, they lie within 1.5 meters to 3 meters. Our third objective is to carry out SWOT analysis. The SWOT, strengths, weaknesses, opportunities and threats, is a strategic decision-making technique used for making recommendations by critically assessing merits and demerits of a given project. We used SWOT analysis for the case of tsunamis generated by Krakatoa volcano and implications for coastal communities in Lampung. By combining field survey results, CG wave numerical model outputs, and published literature, key decision-making aspects are highlighted. This analysis provides new insights for dealing with tsunamis generated by Krakatoa volcano and for developing a detailed disaster mitigation system for Lampung province. The two matrices, left-hand and right-hand side, illustrate the combination of different attributes used. The strengths, weaknesses, opportunities, threats are discussed and put into the matrix form against location, organization, environment, whether helpful or harmful to achieve objectives. Also, strengths against opportunities, weaknesses against opportunities, strengths against threats, and finally weaknesses against threats are discussed. Key points from SWOT analysis. Strengths. The local government of South Lampung has active communication with provincial councils. They have diverse and high-quality fisheries and potential for tourism. Weaknesses. Urban planning in the three villages, East Way Muli, Central Way Muli, Kunjir, is not done properly. relatively poor understanding of tsunamis and their impact on residents. Opportunities. Tourism is one of the main income generation schemes in Lampung province. South Lampung is the main entrance to Sumatra island by Merak Bakahuni ferry. Threats. The capital of South Lampung is about 40 kilometers from the Anak Krakatau volcano, and the nearest inhabited islands, such as Sabesi, Lagundi, and Sabuku, are located within 35 kilometers from the volcano. The area has tectonic and volcanic tsunami-prone status. Based on CG wave model output in Southern Lampung, tsunamis generated by Krakatoa can be destructive and cause damage to residents and infrastructure in future. To conclude my presentation, the CG wave numerical model was applied to simulate tsunami wave propagation due to the 22nd December 2018 Sunda Strait tsunami in Indonesia. Several different offshore wave conditions were considered in modeling past and plausible future tsunami scenarios. Model outputs, for example, wave heights and directions of the 2018 tsunami in Southern Lampung compared with the recorded data at Panjan Tidal Station. Based on the SWOT analysis for the villages in Southern Lampung, we recommend an active collaboration between government departments and local tertiary institutions to disseminate disaster mitigation plans and carry out trauma healing programs for the victims of December 22nd tsunami. The formation of disaster preparedness teams, active focus groups for every village in Southern Lampung and its islands. Review of the existing regional urban planning criteria for future development of infrastructure, for example, houses, roads, boat terminals, fishery ports, etc., which are of paramount importance for the area. Acknowledgements. I would like to thank Global Challenges Research Fund UK for granting funds to carry out field survey activities in Lampung province and numerical modelling at Itera. These photographs were taken during seminar at Itera and field survey activities in Lampung. Please feel free to ask questions or make any comments. Thanks very much.